So question 26 also comes from 8.3, which is direct variation. So solve the problem of joint variation using a constant of variation. So constant of variation is this K. So what we pick up on is, since it says Z varies jointly with W and Y, we're going to have the formula. Z is going to equal this K times this W times this Y. So we'll have a formula that kind of looks like that. And we're going to be trying to figure out what this constant of variation is. So notice how they gave us Z was 504. We don't know what the constant of variation was. They gave us the W was 14. They gave us the Y was 12. So if I do this math here, 14 times 12, that gives us 168. So 504 equals this like 168K, if you will, if I make it a coefficient. So all I got to do is divide both sides by 168. So 504 divided by 168. That's going to give me 3. So the constant of variation is going to be this 3. So this allows me to find Z when I know W and Y. So now I can go Z equals, we have this K times this W times Y. But now I actually have enough information to do this because I know the constant of variation, which is 3. And then W here is 40 times this 6. So Z would equal 6 times 40 would be 240. 3 times 240 looks like that's 720. So 720. So if you want to double check that math, 40 times 6, and then multiply that by 3. And that does give us 720. So question 27 actually gets into 8.4, which is what we refer to as inverse variation. So in our example, a small pulley 6 inches in diameter turns at 1,150 RPMs, revolutions per minute, if you will, and drives a larger pulley at 300 RPMs, revolutions per minute. What is the diameter distance across of the larger pulley? So one of the things we know is, if we understand a little bit about pulleys, is the smaller pulley is actually going to be turning faster. Similarly, the larger pulley is going to be turning slower. So notice how the smaller pulley is going faster. This is inverse concept. We have small to fast. That's inverse thinking, or inverse variation, if you will. Larger pulley, big, but it's going slow. That's inverse thinking. So notice how if one is small and one is big, this is inverse variation. So if I write down this information to start with, we have the 6-inch pulley goes with 1,150 RPMs. Now the key is keeping the units on the same side again. So if I have the pulley over here, keep the pulleys over here. We don't know the diameter of the larger pulley, so 8 X-inches pulley is the larger one, but we do know it's going at 300 RPMs. Now the catch is, when I'm using a proportion to organize, what has to happen is one of the sides of the proportion is flipped when solving an inverse relationship. So when I do this, I'll keep the left side the same, 6 over X, but when I make my proportion, I want to switch the rows of the right side. So the 300 is going to go on the top, and the 1,150 will go on the bottom, and this will give us our setup. So again, notice how we can go 1,150 times the 6, and then divide that by 300. That'll give us the larger pulley, which is 23 inches. And that should make some sense there. So 23 inches is the larger pulley. So it's got to be bigger than 6 because it's the larger pulley. But notice that, there's a relationship here that, 23 is a little over 3 times bigger than 6. It's closer to 4, actually. It's almost 4 times bigger. So notice that if you divide this 300, or if you look at the RPMs, if you divide the 1150 by 4, notice that you should see that that's going to be close to 300 probably. So if I do 11 1150 divided by 4, notice that that is close to that 300. So there's a little bit of estimation that you can kind of play out there to kind of see that. Because look, what I was doing is I was comparing the 6 inches to the 23 inches, and that's almost 4 times as big. So that means if you multiply this by 4, it should get you close to the 1150. So you can also do it that way. You can go 300 times 4 if you want to, as long as you go one way or the other way. Notice how, again, that gets you pretty close to 1150. So that's the catch with inverse variation, is if one's big and one's small, like I said, this is a small and that's a big RPM, then I have a big pulley and a small RPM. That's what we call inverse variation. So for the question 28, 5 machines complete a printing project in 7 hours. How many machines are needed to finish the same project in 5 hours? So notice that if the time went down, that means I have to have more machines. So as I increase machines, time is going down. That's an inverse variation concept. So we're picking up on that 5 machines takes 7 hours. We want to know is how many machines does it take to complete that in 5 hours? So what we kind of pick up on is if I'm decreasing the time, I have to be increasing the number of machines to make that happen. And that's inverse variation. So when I set up my proportion, I can keep the 5 over x, but the catch is I flip the right-hand side. So I have this as 5 on top and 7 on the bottom. So then I can kind of just cross multiply and divide. So 5 times 7, what's 35? And then 35 divided by 5, that's going to be 7. And that makes sense because that would make them equal. So 7 machines would be what we're seeing there. So 5 machines take 7 hours. 7 machines would take 5 hours. So that makes sense there in our answer. So that's what we call an inverse relationship, inverse variation. So question 29, we have a 13-inch pulley turns at 20 RPMs. Find the constant of inverse variation. So we have this formula that y equals k over x, because remember there's this reciprocal stuff going on, this flipping. So this is what we call an inverse variation equation. So notice how the k is our constant of variation. So the 13-inch pulley turns at 120 RPM. So it doesn't really matter, because if you look at this equation, I can write this as y over 1 equals k over x. If I want to find the constant of variation, notice that that's going to be k equals, notice the 1 times k is going to be k. I don't need it. Don't need equal sign there. So notice that 1 times k is k, and I'd have this xy over here. So since they're multiplied together, it really doesn't matter who you call x and which one you call y. So k is going to equal this 13 times this 20. That's going to be the constant variation. So that's going to be inches and also RPMs is all going to be tied together there. So 13 times 20, that would be what, 260? So it's going to be 260. So that's going to be what's called the constant of variation. So notice that the units there would be inches and RPMs all go together there in that constant of variation. So question 30, a 12-tooth gear on a motor shaft drives a larger gear having 30 teeth. If the motor shaft rotates at 500 RPMs, what's the speed of the larger gear? So notice how, again, small tooth is going to have a faster RPM, and the large gear is going to have a smaller RPM. So we should be looking for an answer that is under this 500. So if I note the notation here, I have 12-tooth gear goes with the motor shaft, which is 500 RPMs. And then we have a 30-tooth gear. So it's being driven by the motor shaft, but it's going to be rotating at a much smaller RPM, which we don't know. That's going to be X RPMs. Now, since this is an inverse relationship, because notice how small, fast, big gear lower RPMs. That's the inverse relationship. So when I set up my proportion 12/30, I have to take the reciprocal. I have to flip these. They have to swap rows. X goes on the top, and 500 goes on the bottom. So when I multiply, I'm going to have then this 500 times then this 12. And that's going to give us 6,000. And then if I divide by 30, that's going to give us 200 RPMs. So the larger gear is going at 200 RPMs. So if I was using estimation here, notice that, if I look from 12 to 30, if I double that, that gets me to 24. So that means if this is doubling, then this should go cut in half. So half of 500 would be like 250. So I know the answer's got to be probably around that 250. So 200 RPM sounds reasonable there. So as this one's increasing, this actually has to decrease by that amount. So if this is doubling, this has got to be cut in half. You can kind of see that. Or you can kind of see well, it's kind of more of a 2.5 concept. So I have to divide that by 2.5, if you will. 500 divided by 2.5. That'd probably be a better estimation. You kind of see that hits it right on there. So you can kind of see that going on there too. So as this one is being by a factor of 2.5, this is being decreased by a factor of 2.5 or divided by 2.5. Well, that concludes the Unit 1 walkthrough. I really enjoy, like I said, this direct variation, especially inverse variation. It really makes, especially if you're in machining and things like that, it makes a lot of sense to understand those ratios. Best of luck.